Okay, so is this working?
Yep.
Yeah? Okay. So let me begin by thanking the organizers for the opportunity to give this talk, which will be a very brief summary of some of the previous things that I have done. And this talk is about the problem of time in quantum gravity, which some of you may be familiar with. And the title is Beyond Semiclassical Time, because I want to argue not just in general relativity, evolution is relational, as has been argued not just by Rovelli, but also by Bergman and Kolmar in the 50s, and arguably even Einstein himself. But I want to emphasize that the Hamiltonian constraint of quantum gravity, that the Hamiltonian needs to vanish, needs not be in conflict with Schrödinger evolution. So, here's a brief outline of the talk. We'll talk about classical diffeomorphism invariance and how we can understand the dynamics in a diffeomorphism invariant way, and what is the role of relational observables. Then we'll move on to the quantum theory and discuss how to construct quantum relational observables and a notion of relational quantum dynamics. And I want to emphasize the weak coupling regime of the interaction between gravity and matter, in which a preferred choice of time emerges. This coincides with the usual Bohm-Oppenheimer approach to quantum cosmology, which I will argue is a unitary gauge theory of local time translations. And I'll very briefly mention a phenomenological application, and then I'll conclude the talk. So, oh, this is the old version of the slides, okay. So I think you all know the problems that quantum gravity faces. We need to understand what is the space of states, what is the Hilbert space, what are the observables, what is their dynamics. There is the measurement problem, because quantum gravity is a quantum theory, so we need to understand what is the origin or nature of probabilities in the Born rule. And the question is really how to deal with diffeomorphism invariance at the quantum level. So today I want to focus on this issue in mechanical time models, because all the problems already arise there and I need to learn to walk before I can run. So I want to do that by employing a direct analogy to techniques and concepts used in canonical gauge systems. So the setting here is that of GR. So how can we deal with diffeomorphism invariance? We have a space-time manifold and we have a set of fields. The theory is background independent because the metric is one of those fields, so it should come out as a solution to the field equations. It's not given a priori. Of course, there are some fixed elements, topology, dimension, signature. But the important point is that diffeomorphisms are a local symmetry of the field equations, or if you want, a gauge symmetry, in the sense that if you know a solution to the field equations, you can perform a diffeomorphism to find another solution. And we have already heard about this in Jeremy Butterfield's talk on the whole argument, but the way I want to illustrate this here is a sort of naive gauging determinism that appears in an initial value formulation. So for example, if you have a Cauchy slice on which you want to ascribe initial values to your fields, and you want to evolve these fields to find a solution at later times, you can perform a diffeomorphism to obtain a new solution. But if this diffeomorphism coincides with the identity in a neighborhood of the Cauchy slice, it seems that you obtain two solutions with the same set of initial conditions. And so in usual gauge theories, such as electromagnetism, a simple way to escape this naive indeterminism is to declare that observables are gauge invariant, like the electric and magnetic fields. So it would seem that if we want to apply this reasoning to general relativity, observables should be diffeomorphism invariant. But what kind of diffeomorphism invariants have a nice interpretation? These are the relational observables. And the idea is that observers, they record the dynamics in local regions of space-time by performing experiments with a set of reference fields that function as generalized clocks and rods. Okay? And the outcomes of the experiments are the values of the fields that they measure relative to the clocks and rods. And these outcomes are the relational observables. So the relational observables are the outcomes of the experiment. And these observables, they completely encode the dynamics in the region of the experiment. They are conditional quantities in the sense that they yield predictions, the values of the measured field, relative to a certain condition, which is the observed value of your clocks and rods. And because they only make reference to relations among field values, they make no reference to an abstract space-time point, so they can thus be seen as constant scalars on space-time. That's why they're invariant. Constant scalars are invariant. And that's why Hovelli calls them evolving constants of motion, because they're constant scalars. So let's see how this works in the simplest example, which is of a 0 + 1 dimensional space-time. It's a world line. Now it's a particle trajectory. In this case, choosing a clock on the trajectory amounts to choosing a field and finding a diffeomorphism for which the pullback of this field is the identity. What does that mean? It means that the level sets of this field tick away, or they mark the points on the world line. Now, if you want to describe the dynamics of any other tensor field in the space-time, there's a relation observable for that. It is a constant scalar, so for every point in space-time, it gives you the same value, which is the pullback of your tensor field, evaluated at a certain clock instant. Now, this is a very formal definition. You can do much with it. It's much more convenient to rewrite this observable as an integral over space-time. In this case, an integral over the world line, where you have here your tensor field f, can be whatever tensor field you want. You have a gauge fixing delta function that fixes your clock instant, and you have a determinant, which is the very famous Fadev-Popov determinant that people use all the time when they want to fix the gauge in a path integral. But this is a completely classical construction. And using this integral formula, you can show by direct calculation that these objects are diffeomorphism invariant. So what I want to do is to translate this classical construction to the quantum theory. So let me skip this for now, because I actually changed the slide, so this is an old version. So in the quantum theory, we have the energy eigenstates, and we can also define the proper time states, which are conjugate to the energy eigenstates. Now, of course, in general, these states are not orthogonal, because in general, you cannot define a self-adjoint time observable. But this is not so important here, because I want physical states to be superpositions of the no energy eigenstates, because I want them to be annihilated by the Hamiltonian. Why? Because diffeomorphisms of the states are proportional to the Hamiltonian, so if they are annihilated by the Hamiltonian, they are diffeomorphism invariant. Now, the inner product between two such physical states, it's a very simple calculation to show that the integration over the proper time factors out. You have a projector at an arbitrary instant of proper time. And so this is like the Fadev-Popov regularization of path integrals, in which you have a gauge fixing condition, and the volume of the gauge group factors out, and you can throw it away to regularize it. So just as Fadev-Popov regularized path integrals, you can regularize the inner product in this way. And the idea is that the space of solutions of the Hamiltonian constraint that are normalizable with respect to this regularized inner product is the physical Hilbert space. And now the idea is, just as in a path integral, you can insert a field to compute an expectation value. I want to define the relational observables by insertions of tensors into this regularized inner product. Now, this is a vague and heuristic idea. To actually make it rigorous, you have to have a complicated definition, well, maybe not so complicated, of the relational observables. I do not have time to fully motivate all the factors here. I just want to say that in the case in which the spectrum of the Hamiltonian spans the real line, this formula here reduces to the classical integral expression that I showed you before. And even if the spectrum of the Hamiltonian is completely general, it could be discrete, it could have continuous or discrete parts, these observables have the correct dynamics, which is given by this formula. What this formula tells you is that the clock derivative of an observable is the observable of the clock derivative. And exactly the same equation holds in the classical theory if you replace commutators by Poisson brackets. Furthermore, this definition tells you that the statistics of relational observables is a conditional one, just like the classical observables are conditional quantities, because if you insert this expression here into the regularized Fadev-Popov inner product, this reduces to the definition of a conditional expectation, or a conditional correlation function, where the condition is your instant of proper time. So this can be seen as a generalization of the famous Page-and-Wouters approach, which uses also conditional probabilities. In this context, I also mentioned the work of Philip Hearn and collaborators. They have a different formalism that achieves similar results, and it would be interesting to compare the two. So this is very nice, and I can suggest a tentative set of postulates. I will not read the whole thing, because this is just standard textbook quantum mechanics, but transposed to the situation in which you don't have an absolute time, but you have many clocks. So the idea here is that what you observe are relational observables. So the Born rule should be with respect to eigenstates of the relational observables. And if you have any hope of having a consistency between different choices of clock, then a change of clock is a change of basis in the physical Hilbert space, just like a change from momentum space to configuration space. And in this formalism that I have shown you, this can be done, because the observables, they are automatically symmetric, and depending on their domains, if they have self-adjoint extensions, they automatically have a complete set of eigenstates, and you can do this change. Now, what about our universe? There is very little hope in realistic models that you can actually solve the constraint, and that you can actually find the observables, and let alone determine whether the dynamics is unitary. Well, in that case, I suggest that we do what we always do, which is perturbation theory. And this perturbation theory is a weak coupling expansion. I will go back a few slides, because again, I changed the slides, but this is the old version. So the weak coupling expansion, now going back to the classical theory just to illustrate it, in general relativity, the Hamiltonian has this structure here. It is a Hamiltonian for the gravitational part plus the matter part. And you have a coupling constant, which is the Newton coupling constant. This is analogous to a relativistic particle, where the coupling constant would be 1 over c squared. The idea is, if you cannot solve this exactly, you can do a WKB expansion of the on-shell action, which solves the Hamilton-Jacobi equation, in powers of this coupling constant. What you find to lowest order is the no coupling limit, that matter and gravity are not coupled. So this is the analogous thing to the non-relativistic limit. And in that limit, you can define the gravitational proper time, which is simply the proper time along the trajectory of the metric in field space. And to higher orders, you find that this gravitational proper time controls the dynamics of matter, because the on-shell action of matter obeys a time-dependent Hamilton-Jacobi equation with some corrections that are proportional to the matter Hamiltonian. Now, this gravitational proper time is a choice of gauge, of course. The theory has freedom to choose time parameters. So this choice of gauge has an associated Faddeev-Popov determinant that you can also compute in perturbation theory. Now, if you go to the quantum theory, you can do exactly the same thing. In the quantum theory, you have also a constraint, and you can solve it perturbatively, if you cannot do it exactly, by doing a WKB expansion of the wave function. And this goes by the name of Born-Oppenheimer, a semiclassical approach that has been analyzed by several groups, including Klaus Pfeiffer and Professor Sink, who's here. And what you find is that the dynamics of matter is controlled by a corrected Schrödinger equation, in which, just as in the classical theory, you have powers of the matter Hamiltonian appearing in the corrected in the corrected effective Hamiltonian, and the wave function is rescaled by the Faddeev-Popov operator, or by the square root of the Faddeev-Popov operator. This is just a calculation that you can do directly from this weak coupling expansion here. Now, this equation here implies a unitary dynamics with respect to the standard L2 norm of the rescaled states. But in terms of the original states, so the states that solve the Wheeler-DeWitt equation, you have appearing here the Faddeev-Popov operator. So this is a gauge-fixed inner product in which you have the Faddeev-Popov measure, as you would have in a gauge theory. So this means that this Born-Oppenheimer semiclassical approach is unitary, because the norm is conserved under the dynamics, and it is gauge-fixed. It's a gauge-fixed theory. The probability density associated to this inner product is conditional, because it makes reference to an instant of the gravitational proper time, And the relational observables, again, can be obtained by suitable insertions in this inner product. You can apply these ideas to the early universe, and I refer you to Chataignie's talk tomorrow. For example, you can consider a very simple model of a deciduous background with some Sasaki perturbations. You apply this weak coupling expansion. You find a corrected Schrödinger equation for the primordial perturbations. And you can apply this Schrödinger equation to find well-defined and unitary corrections to the primordial power spectrum. So just to conclude, I have very briefly sketched for you a formalism for the systematic construction and interpretation of relational observables in the classical quantum theories in a model-independent way. The relational observables have the correct quantum evolution, and if they have self-adjoint extensions, this implies the unitarity of physical propagators. Changes of reference frames in this case are changes of basis. The weak coupling expansion of the Born-Oppenheimer approach is a unitary gauge theory and leads to unitary corrections to the dynamics of matter. And of course, there's many things that you can do now. You can apply this to slow-roll models. Again, see Chataigni's talk tomorrow. In field theory, I think we should stop looking at ad hoc definitions of the wave function of the universe, and we should look at the path integral as defining relative initial data, so initial data for a relational initial value problem. And who knows, maybe a formalism like this can pave the way to the emergence of the Born rule, also in a diffeomorphism invariant context. Thank you.
Thank you. We have time for a few questions.
Just a curiosity.
Yeah.
What is the difference with respect to the relational approach which is used, for example, in loop quantum gravity, where you also have initial Hilbert space, then you have the Wheeler-DeWitt equation, and you constrain to the physical Hilbert spaces, similar as you have done.
Right. The approach that is usually used in the literature, including loop quantum gravity, but not restricted to loop quantum gravity, is not model independent, because it depends on the structure of your action, essentially which fields serve as a clock. For example, there usually a scalar field is used, sometimes even a massless scalar field, which is very unrealistic. This here is model independent because that formula there, in principle, can be applied, this formula, can be applied to any model if you know the spectrum of the Hamiltonian.
Even to loop quantum gravity.
Even to loop, I haven't done this for loop quantum gravity, but I think in principle it could be done. Although it would be very difficult, let's say loop quantum cosmology maybe.
See, and do you think, because at the end you use perturbative techniques, do you think this can help to employ perturbative techniques in that context where typically it's very difficult?
In which context, sorry?
Like loop quantum gravity, for example, where
Yes,
they don't use perturbative.
No, absolutely. I think this weak coupling expansion is essential because the argument that has been done first by Lapshinsky and Hubakov in 1979, then by Banks in 1985, and then again Vilenkin, and then Klaus Kiefer and T.P. Singh, and many people. The argument is that this weak coupling expansion, at the lowest order, you get the usual Schrödinger equation for quantum fields in a curved spacetime, which is what we observed. Well, we observed a flat spacetime, but okay. So this weak coupling expansion is essential if we want to make contact with the physics that we already know. And also because in realistic situations you cannot solve the constraint exactly.
Okay, thank you.
Thanks. If I can just summarize part of your construction to arrive at diffeomorphic invariant quantities. I can put it in terms of concatenations of field values, where one field takes a certain value, another field takes a certain value.
Yeah.
And given sufficient asymmetry, that is going to uniquely pick out a region of space-time. But what happens in the presence of isometries? I just wonder how the construction goes there. And if I could just throw in a related question, it may be that diffeomorphism invariance is a very special kind of symmetry, but normally where we've got gauge symmetries, you want them to be, you don't want the states, space of states, you don't want the states to be gauge invariant because you want those gauge symmetries to connect with other gauge symmetries in elegant and beautiful ways.
Right.
So I just wonder about that. Yeah.
Right. So for the first question, I have not carefully looked into the case of isometries, but I will give you this answer. As you see here, this is not an integration over the whole of spacetime, or in this case the world line here. This is an interval of the world line. This is sufficient for this definition. And how do you choose this interval? You choose this interval when your clock is monotonic with respect to proper time. And so in this construction, the only thing that matters is if you have fields that in a certain interval are monotonic. That's it. And so in principle, you can apply this in general. And I say that in principle, of course. Regarding what was the second question? Sorry.
Sometimes, very often in physics, we want to...
Yes, the states are not H invariant. Yes, absolutely.
Yeah.
So I here applied the usual Dirac quantization, which says the constraints have to annihilate the states. And I wanted to see how far we can go with that. Now, I absolutely agree with you that this may not be the best approach. Well, there's one argument in favor of it, which is if you define a diffeomorphism, a diffeomorphism invariant path integral, you can show formally that it satisfies the constraints. So if you want to define your quantum gravity via path integral, this path integral should solve the constraints. This is one argument in favor of it. Now, there's a very simple thing that no one pays attention to. It's a paper by Kolmar in 1979, in which he argued that if the constraint is not self-resolved, you could have evolution and the constraint simultaneously. And so I think we should maybe relax this condition, also because of what you said. We need to include other gauge symmetries. The only gauge symmetry here is diffeomorphism invariant. I haven't said anything about Young Mills or electromagnetism and so on. So I do think we should relax this, yes.
Thank you. We have to move on to the last talk.